This lecture introduces Monte Carlo sampling, an approach to getting expectations and probability distributions when the probability distributions are very complex and difficult to obtain through closed-form solutions. We'll first talk about the basic concepts in sampling, and then we'll talk about a specific approach that illustrates how these techniques can be used for approximating complex and difficult distributions and expectations, and this approach is known as rejection sampling. So why do we use sampling and Monte Carlo methods for Bayesian machine learning and Bayesian inference generally? Well, you can consider the problem of finding the expectation of a function, which we want to do with respect to some distribution, say p of x. And we want to do this in Bayesian machine learning if we want to minimize the loss. For instance, the expectation, the function that we are interested in is a loss function, and we want to minimize it with respect to a posterior distribution. The variables in this may be discrete, continuous, or both. We'll consider the continuous case throughout the rest of our discussion because it's a fine example of what we're dealing with. So the expectation then, of course, looks like this. It's just the integral of the function we want the expectation of times the probability density and then integrated over all values of that vector x. For many real problems, unfortunately, the evaluation of the integral is intractable. And we actually saw an example of this in our previous lecture when we talked about latent Dirichlet allocation. We came up with a nice model, Bayesian model for text that we could use to understand the discovery of topics in text. But unfortunately, the approach is not tractable. We can't evaluate the expectation of the integral necessary to solve that problem. So we need to use other methods, and one of the methods that we use for this solution is sampling. And in general, the dimensionality of the parameter or latent space can be too large for us to do traditional sampling approaches and traditional integration approaches. The complexity of the distribution can be very difficult, which is what we saw in the case of the latent Dirichlet allocation problem. And in general, the required integrations may not have closed-form solutions, and numerical integration is not practical for a lot of reasons. So the basic approach then is to draw a set of observations x from this distribution p of x, and typically we draw them independently. Although in our next lecture we'll see how we can get actually a better answer without assuming independence. So with this set of x's, we can approximate the integral that we're using to find the expectation of the function f of x by finite sums over this sample that we've obtained, and we'll call it m samples. So we've obtained these m samples, then we can evaluate at the function, and that'll be f of x, for each one of those samples indexed by m, little m, and then we take the average of that in order to approximate the value of that expectation. And we know from the law of large numbers that the expectation of this approximation, f hat, will actually go to the expectation of the true underlying function as we get enough finite sums. In other words, as we get enough samples by increasing the sample points across the space for the function. And the variance of the estimator also behaves nicely. It goes to 0, which is good. So the variance of this approximation actually, as we get more and more samples, is going to go to 0. Okay, well, there are a number of sampling issues that make this approach to finding the, in general, the integral or finding the expectation too complicated for this direct sampling. The function transformation, which we use in a lot of cases for solving these kinds of problems, only works well when we can invert an integral. And typically in complex problems, we can't even solve the integral, much less integrate or invert it. Grid sampling, which is this notion of breaking our sample region up into a number of points and this sampling there at evenly spaced intervals, turns out that's very inefficient. It's inefficient because we tend to oversample in areas where our target distribution, this P of X, is small, and undersample where it's large. And as a result of that, we can get inaccurate answers. So there's some approaches that are typically taken. One is rejection sampling, and that's the one we're going to talk about in this lecture. Another one is importance sampling. We won't talk about it, but again, if you get the ideas of rejection sampling, you can learn importance sampling. And then there are extensions to that, sampling, importance, resampling, another technique, and Markov chain Monte Carlo, which is the most effective technique, and that's what we will introduce in our next lecture. So we're going to talk about rejection sampling in this lecture as a way to motivate and give you an idea of how Monte Carlo sampling works, and therefore set the stage for MCMC, which is the real powerhouse for what we want to do in Bayesian machine learning. Okay, so let's take a look at rejection sampling, which is hard to invert. So this is the distribution that we want to sample from because we want to find either the expectation or we want to basically model the distribution itself and sample from it. So we assume that it is, however, easy to sample from it at x, possibly up to some normalizing constant. So what we're showing here is that we're going to let p tilde of x be the kernel of the density that's easy to evaluate, but the normalizing function may be unknown. So it may be a complex function, but we can sample from at least the kernel of that density function. So the way that rejection sampling works is with a simpler distribution than the complex one that we're talking about, which actually is the distribution that we can draw samples from. So while we can evaluate with the kernel of the target distribution, we can't sample from it. So we need a simpler distribution, and we'll call that simpler distribution Q of X. And the name for this is the proposal distribution because it's proposing a sample point. Okay, we're going to grab some constant k, and what that constant is going to do, it's going to make the proposal distribution an envelope for the target distribution. So k times q of x is going to be an envelope, which means it's going to be greater than all values of p tilde of x, the target distribution kernel that we're interested in. And this is true for all of x. And then k times this proposal distribution is called a comparison function. So here are the steps then for rejection sampling for a univariate distribution. We generate some point, say a starting point, from our proposal distribution. We generate a value that's uniform, so we're going to draw a uniform value, and that value is going to be uniform between 0 and the comparison function point. So the value of the comparison function at x0, the point that we've generated, the sample point that we've generated. And if this uniform point that we've drawn is greater than our proposal distribution, at least the kernel of the proposal distribution, then we're going to reject the sample. So we're going to throw away x naught and look for another sample point. Otherwise, we're going to retain it. And we're going to keep this idea and repeat it over and over again until we get a good sample. So here's a picture of what it looks like. This is a rejection sampling example, and the dark line that's multimodal is an indication of our P of x. So there's our target function. That's our target distribution that we want to model. And I've drawn it here multimodal to say that it could be complex. It could have all sorts of weirdness to it. And we're going to create this proposal distribution, Q of x, and I've designated that with this green line, but I've actually shown what it is when we create the envelope, which is multiplying by k. So that's k times the proposal distribution. which has got a nice shape. It could be a Gaussian. It could more likely it's a Cauchy or a T distribution. So we're gonna pull out a value from it, and we're going to use it to sample. Okay, and we have a sample. So where the vertical line is our x0 point, and that point then is basically what we're sampling. We're sampling at x0. And we look at the value then of a uniform draw between the x-axis, between 0, and all the way up to this k times the proposal distribution, the envelope. And so we're going to draw a uniform in there. And in this case, the uniform that we drew is less than p of x. So we're going to keep it. We're going to keep the value. If it came out above the value of p of x, in other words, between p of x and k times q of x, we would reject it. So you can see very clearly where the acceptance region is. It's all the points along that vertical line that are less than p of x. And that's the area in which, that's the acceptance region that are less than p of x. And the points that are above p of x, between p of x and k times q of x, the proposal distribution, the envelope created by the proposal distribution, that's the rejection region. Okay, so you can see very clearly where our acceptance and rejection region are. From this example, it's apparent that the choice of k, which defines the envelope function, is important, but let's try and make this a little bit more precise. So we note first that these x values that are the sampling points are coming from this proposal distribution q of x. And they're accepted then with some probability p tilde of x, the target distribution value, over the value of the envelope, k times q of x, the proposal, because this is how we've defined the uniform distribution from which we're making the acceptance-rejection decision. So this means we can define the probability that a sample of these points is going to be accepted, and that probability of acceptance is going to be just that acceptance probability, that p tilde over kq of x, times the density function, the likelihood that we choose a point at x, and we're going to integrate over all values of x. And notice that in that integral that the q of x's cancel out, and we're just left with 1 over k times the integral of p tilde of x. Now, if this were truly a distribution, that would just integrate to 1, and we'd be left with 1 over k. But we've pulled out the normalizing constant, indicated we don't necessarily know what it is, and all we've got is the kernel of the distribution. So we're left with something then in that integral which is less than 1. Okay, so the proportion of points rejected depends on k. From this, it's obvious it depends on k. And we want it as small as possible, and the reason we want it as small as possible is because that's going to define our acceptance region. And the closer we get it to p tilde of x, or in this case we've written as p tilde of z, the closer we get it to that, the better. So in z here, we're just using as any particular variable that we've got in our distribution function. So it's clear then that we want this kq of z, obviously by definition, has to be greater than the target distribution p tilde of z, but we want it as close as possible, and we'd like to keep k as close as possible, or as small as possible to make that happen. So to be effective, this comparison function must be close to p of x. That's the bottom line. Our envelope has got to be as close as it possibly can be. Multimodal distributions are challenging for envelope functions. It's very difficult for us to create these for these multimodal distributions. The example we gave was a multimodal distribution, and it's hard to know exactly which mode is the one that we want to target as the peak. So we actually have to find the maximum within those multimodal distributions, target it, and then make sure we're covering the others. It's also the case that this rejection sampling approach is not very effective for high dimensional distributions, and we can see this with a little example. Suppose we've got a target distribution, which is a multinomial Gaussian, and it's given by, let's say it's centered at the origin, and it's got some constant variance that defines its variance covariance function and zeros in the off diagonals. So it's just going to be some constant sigma squared p times the identity. And then we can define a Gaussian envelope, same kind of thing, multivariate Gaussian. It's clear that that this constant that we've defined for the variance variance component in our target distribution must be less than the one for the proposal distribution, because that's what's going to be required in order that we get an envelope to fit it. Because if we don't have that, then it's going to be very hard for this to find a k that's going to work for all points. We can't find a k. To be honest, that's the point. You can't find one that'll work unless that variance inequality is true. So in d dimensions, the optimal k then is going to be given by the ratio of the variance or the standard deviation of the proposal distribution to the target distribution, and it's taken to the power of d, the number of dimensions we have. So that's the optimal k for the acceptance region that we want, and because the acceptance region is going to be defined by a ratio of volumes, the volume under p of x and the volume under kq of x, and that ratio then is given by 1 over k. Note that this diminishes because now it's going to be taken to the exponent of d, and that's going to get smaller and smaller as d gets large. So that means that our acceptance ratio is going exponentially to something that's quite small, which is not good because we want the acceptance region to be as large as we can possibly make it for our distribution. And we can see in these multidimensional cases, it shrinks exponentially. However, despite that fact, rejection sampling can be used as part of a larger approach to sampling in higher dimensions, and it is used for those kind of problem spaces. And it's also, as we pointed out at the beginning, a good way to illustrate how we do Monte Carlo sampling in order to capture complex distributions.